folks, let's get going. Mathematical methods in chemistry. Is everybody in the right place? Good. Okay, first years, welcome to Southampton. It's probably a nice course to start with because this computational chemistry business is our strongest side. So the supercomputer here at the university is the biggest university machine in the country. So if you're doing computational chemistry, that's the right place to do it. The other thing about it is if you are a kind of chemist who doesn't like smelly fume hoods, but who likes Hollywood-style 3D molecules on the screen, this is also the right module. Strangely enough, Hollywood is mostly correct in how they depict computational chemistry. You will have molecules in 3 dimensions on the screen, big supercomputer. And so this module is about the basic mathematics that will prepare you for quantum chemistry calculations, molecular dynamics modeling, that is used rather a lot in modern pharmacology, materials engineering, drug design, structural biology, and so on. It is these days actually easier to calculate things than it is to measure them experimentally. So what I'll do today is, this first lecture is introduction. It's not examinable, it's just a movie, sit back and enjoy. The real horror will begin on Thursday, where this is the first and the last PowerPoint lecture, by the way. Everything else is chalk and talk on the board. So it's a very difficult course, but this first lecture is just a wishy-washy introduction into what it is and why we should do it. So what is computational chemistry and what can we do with it? Well, turns out chemical systems can actually be rather nasty. There are molecules you'd rather not have in the lab. There are things you would not be permitted to do these days with chemical systems. And there are cases where, well, it's plain silly to just even try and do something. This is octanitrophenane, a famous explosive, probably the strongest explosive by energy per unit mass that it is possible to have in chemistry. It's been predicted computationally and then synthesized, and it does the job perfectly well. But if you ask yourself the question, well, I'm a synthetic chemist who would think about synthesizing octanitrophenane. It's not at all obvious how to cook such a molecule, and so various possibilities have to be weighted and tried. And you'd rather not do it in the lab, because some of those possibilities might be rather unstable, and then it would be best to just run a calculation to see what's the best way of doing it. This is VX, probably the strongest military nerve agent in current widespread use. It's an acetylcholine hydrogenase blocker. And again, the lethal dose is somewhere around 10 milligrams. And it's not a good idea to have that around in the lab, even with all the safety precautions and so on. Or it could be, well, some plutonium complex in here that is used for extracting plutonium from fuel rods. You can just about see, it's not a very good picture, it's an X-ray crystal structure, bunch of oxygens coordinating to the plutonium in the center and this cage around it to keep it inside. But again, plutonium is very strongly gamma radioactive, and so it will take a meter of lead to really make it safe, and it's probably a good idea to do as much of that work as possible computationally before you are trying to synthesize something like this in the lab. Or the reasons might be rather more pragmatic. Certain molecules are just plain expensive. We have to order things from the manufacturers, from Merck, Luca, Sigma Aldrich, and so on, the great big companies that make all these chemicals. And this is an example of a really expensive molecule. It's an N-fullerene. Somebody synthesized the fullerene, C60, then chemically cut the cage open, put a water molecule inside, and then stitched the cage back. Now, fullerene itself is about 1,000 pounds a gram, and by the time you've done this complicated procedure, these things are probably in the millions of pounds per gram. They're used for complicated quantum mechanical research because the properties of the molecules inside those fullerene cage are described by quantum mechanics. And it's also a great idea to not spend too much public money on them. This is a butterfly pheromone. They use it to attract each other, but they use tiny concentrations. So in order to get an even you have to catch and blend about a kilogram of butterflies, which is, you know, a bit gross. And so again, modeling it before you do it is a good idea. This is a platinum-based catalyst that catalyzes the formation of silicon-carbon bonds in situations when you need that. Again, just plain old expensive. So they can be dangerous and they can be uneconomic. The other category of chemical systems that you would not be allowed to experiment with is the cute ones. Right? It's not a good idea to experiment on something like that, or on something like this, or on something like this. If you're a pharmaceutical chemist looking for a substance that will block a particular broken enzyme in your body, and if you start doing experiments, screening, for example, a library of several million molecules on several million rodents, you'll have a crowd with pitchforks and torches at your door. Right? Again, not possible. Therefore, the pharmaceutical companies first run calculations on large supercomputers to narrow the choice down from several million to maybe a couple of hundred molecules, and you would be permitted to bother a couple of hundred mice if you have a good enough reason to do that. So again, certain chemical systems we cannot experiment on. And then, of course, the systems might not even exist to begin with. They might be hypothetical if you're looking for some complicated reaction and some strange reaction intermediate in it, possibly short-lived, couple of microseconds or even nanoseconds. It would be impossible to stabilize, impossible to isolate. It just transiently exists on the way to somewhere. The only way we can stop time is if we are in control of that time. And this can only happen inside a supercomputer. You haven't missed much, it's an introductory lecture, and you're in the lecture. Things like protein binding ligand candidates, if you're making a drug molecule and you've got a few million candidate molecules, see what binds in the supercomputer, then do the experiments. We'll save you time, we'll save you money, we'll save you personnel expenses. And then serious exotica like magnetic systems, so molecular magnets and electronic devices, exotic electronic configurations, exotic magnetic properties, and so on. Such things, it is possible to A, predict and B, rationalize only computationally, because you cannot have atomic level control over every material in physical reality. You can, however, do that in virtual reality. So summary for this is it's actually faster, cheaper, and more accurate in quite a few cases these days to compute than it is to run experiments. And as you know, computers have made colossal advances in the last 30 years or so. It all went from punch cards, you know, a couple of thousand multiplications per second, to a couple of billion computations per second in your laptop and phone, and a couple of trillion in any serious computer that you have. So by at least 6 to 9 orders of magnitude, the machines became faster in your lifetime. And chemistry has reacted appropriately to that. We now compute rather a lot. So this enormous map, so I have to zoom it out so much, is because it is a complete, well, they claim it's complete, I rather suspect a few things are still missing, map of human metabolic processes. This is every significant chemical reaction that happens in your body. And if you zoom in on this tiny little pixel, it's a chemical substance. Now, if we are doing metabolomic research, how the body responds to poison, how it responds to changes in the diet, what to do about things like phenylketonuria when the body cannot synthesize its own phenylalanine, and so on, we are looking at this complicated metabolic network. As the second and third years here know, every single reaction is a differential equation where the rate of production of some reactant will be proportional to products of concentrations of other reactants. If you have a million molecules in here, you would have a few million reactions between them. So you have a colossal system of coupled differential equations. And so to even start to model that, you need a supercomputer. It is impossible to do such things by hand. It is, however, the daily requirement of nutritional and metabolomic research. And every single reaction is such an equation. If you describe this graph as a mathematical object called a graph, then it's an edge, and of course every single reaction is some complicated quantum process that is happening there. So I mentioned quantum mechanics a few times, and this is because that subject is actually central to chemistry these days. We are not so much pouring colored liquids from one flask to the other, as the first years will soon discover. It's actually fairly brutal math, most of it. And the fundamental equation that describes reality here on Earth at reasonable energies is called Schrödinger's equation. You will see that in your second answer here. But it's a horrendous looking partial differential equation where this strange inverted nabla is a bunch of derivatives, and you have things like electron momenta, like energy of the moving nuclei, attraction, repulsion, and so on, and a strange object called the wave function, which Schrödinger introduced. Now, as you can imagine, solving this might be involved, particularly if derivatives are there, and it's a strange type of equation that first years haven't seen yet. It is not equation for a number, right? The equations you're used to are the equations when the unknown is a number. In this case, the unknown is a function. And this is a bunch of derivatives, and multiples multiplied into a function are expected to produce exactly the same function in the end. Not an obvious thing to happen. This is a very strange thing. So this wave function business is a complex. So it's not a real number, it's a complex number, it has an imaginary component. It's a solution to this horrendous equation in here, and it has a very strange property in that it contains complete information about all conceivable property of some chemical system, including the past and the future. So this was a bit of a shocker when this was proposed in 1905. It is rather hard to believe that such a function might exist. Strangely enough, it does. And as you can imagine, it is rather hard to compute. You would need a very big supercomputer. However, the examples of wave functions all of you have already seen. The atomic orbitals, all those S, P, D, F, and so on, all these strange shapes that you were using for hybridization and so on, for explaining covalency, donor bonds, and so on, they are actually geometric plots of wave functions, and this is where they are coming from. Your school textbook did not actually tell you where the orbitals came from. It told you, well, okay, we've got these atoms, we've got these strange things sticking out of them. What these strange things are actually probability densities corresponding to the wave functions that have been computed using this equation. And by about the end of your second year, we will explain to you how that is done, but that's necessarily a very mathematical and very computational task. And you can take my word for it, you will be at a considerable advantage relative to your peers who didn't take that course by about the middle of your second year, because our quantum chemists don't take any hostages. They will dump a lot of mass on you, and you better be prepared, and we will prepare you to that. So, of course, these atomic orbitals are not the only types of orbitals possible. This is an example of a molecular orbital of a fully remote molecule. This is something that we will teach you how to do. But again, this is a function in 3 dimensions, and this is some probability clouds of where electrons can and cannot be. Writing that down with a pencil is clearly impossible. The function is too complicated, and so we have to use a computer to do that. Now, the software that does it, and I will briefly show you the package that we have here at the university, is really expensive. It starts at thousands of pounds. And this is what you need a lot of mathematics for. Simple cases can be done analytically. If you're looking at a bond between a pair of atoms, it's an analytical solution, it's a function, we'll show you how to get it. However, if you're looking at a real-life system, then it has to be computational. And then what can we do with that? Rather a lot, it turns out. We can create a little chunk of virtual reality, put the periodic boundary conditions, so if you move out of one edge, you reappear from the other, set up Schrödinger's equation in that 3-dimensional cube and flick the switch. It's like, Genesis. You say, let there be light, and send a photon into it, and there will be light. So it's a pocket universe that you can play with. So here's a little peptide you can barely see, and of course the only reason anything ever dissolves is the energy of salvation is greater than the energy of crystallization, so it goes into solution. And so this is an example of a calculation of how a peptide is salvated by a lot of water molecules, where the hydrogen bond and so on. It is clearly impossible to actually do this experimentally because the wavelengths of light in a microscope is much bigger than the molecule. And this molecule is maybe a nanometer across, and the wavelengths of the light is 400 nanometers, and of course anything smaller than the wavelengths you by definition cannot see. So there's no conceivable way you can actually optically visualize any of this except inside the computer. That's lysozyme, a very common protein in various bodily fluids. It's there for the purpose of killing bacteria, and as you can just about see a drug that's bound to it, and if your purpose is to block a particular functionality of a particular protein, this is how you do it. You drop it in virtual reality, you see if it binds. If it binds, that's your drug candidate experimentally. Catalysis, platinum is expensive and hard to use, very chemically inert, very high melting point, and so on. But that's a platinum nanocrystal inside virtual reality, and you can try and bind things to it and see how hydrogen dissociates on its surface. And it turns out that the hydrogenation catalysts involving platinum only have a few catalytic spots. And if you expose the wrong surface of platinum, for example this, well, nothing's ever going to happen. It only happens on certain stages, but not the others, and this is what we use computational chemistry for. This is a fibril, a protein aggregation fibril of the kind that you get if you have the mad cow disease, Alzheimer's disease, and certain types of neurodegenerative disorders. Some proteins misfold. These misfolded proteins aggregate into long fibrils. These fibrils clutter up the cytoplasm in the cell, resulting in impaired function and cell death, and the slow and unfortunate process of neurodegeneration. Again, this is not an atomic detail like here. This is rather crude. This is a contact surface of the molecule, but this is done, this three-dimensional reconstruction is done by taking millions of electron microscope photographs from different sides and then reconstructing a 3D object that these photographs are showing. Again, if you think about how much computational effort this takes, well, you have about 100 pixels this direction, maybe 100 pixels into the depth, couple of hundred in here. That's already a few million pixels. If each pixel takes a byte, that's already a few megabytes of data, and in practice a lot more. A million photographs will take another couple of gigabytes, and suddenly you discover that you have a serious computational problem. And then we can take it to absolute extremes. This is the current state of the art, where you can have atomic level 3D models of whole organisms. Tiny ones, so far, like this tobacco mosaic virus, but it is possible to just put it into virtual reality flexes, which at the moment the time runs rather slowly in virtual reality, like you can do a couple of nanoseconds at most. It's computationally expensive, but you do have a living virus inside a supercomputer with some approximations, but it is possible to do these things. So this is something they don't tell you at school. This is something they do not tell you in your introductory chemistry courses, first and second year here at the university. This is research-grade chemistry that we do on real computers, and this course is about equipping you with the necessary mathematics to be able to do all of this. Of course, all these pretty pictures are all great and fine, but as you can imagine, even visualization of that on the screen is a partial differential equation that describes the lighting of a three-dimensional object from a particular direction. So we are pretty comfortable as computational chemists with modeling things that involve reasonable energies and reasonable velocities, but if you actually look at inner electrons of gold, plutonium, uranium, and so on, turns out they're so close to the nucleus and the interactions are so strong that they move close to the speed of light. So you actually have relativistic effects for the inner electrons of heavy elements, and even that can be incorporated. In fact, gold is yellow because of the spin-orbit coupling. It's a relativistic effect. And I'd say as of 2015 to 2018, computational chemistry can reasonably handle almost any chemical system inside a computer. instead of ins plus. Of course, much faster, much more convenient, safer, cheaper, and so on. So here's an example of a bunch of guys in Japan at a supercomputing center who have modeled the cytoplasm of a living cell. So it's a huge computational effort. What they put in is every protein and piece of DNA and RNA that the cytoplasm is known to contain. So they don't show you the individual atoms, they just show you the contact surface of a protein, but the various metabolites are shown as atoms, and they remove the water. Right? So obviously all of this is filled with water molecules, but you wouldn't see much if you leave the water in. So when they visualize this, they just took the water out of the visualization. So this is a real-time molecular dynamics simulation in a large supercomputer of the various proteins and the associated metabolites like ATP, sugars, and so on that you have bound to those proteins. So here's a froze time. And in fact, you can see that most of the cytoplasm is not water. Cytoplasm is fairly densely packed with various dissolved biomolecules. So it's a highly concentrated solution. And this is when they put the water back. So of course, you don't see much. All of them are solvated, so they'll just put the solvation water on in quartz, the molecules. But again, it's not, you can't see much if you leave the water inside the visualization. And so these proteins, they aggregate, and this is one of the famous ones. This is ribosome. This is what synthesizes proteins once it receives the RNA that has been transcribed from the DNA. It's a very large molecule, and once something comes out of a ribosome, it comes into this chaperone system. It's called GROEL, which makes sure that the protein folds correctly. And you can watch this process in real time. It is not possible to do it with optical microscope. These things are smaller than the wavelengths. It's not possible to do it with electron microscope because you have to freeze it to near absolute zero, at which point the biology stops. But it is possible to observe it in a supercomputer. So that's your ATP, right? There's 3 phosphate groups in there and the adenosine that it's bound to. As you know, this is the energy currency inside the cell. And so here's ATP binding to an enzyme. It will get itself dephosphorylated. The energy that is released will be used to drive the metabolic process in the cell, and this is an active site. So all of these are atoms, they just hid them behind the surface so that these things are visible. So another large protein, so pyruvate dehydrogenase, that is an essential component in glucose oxidation in your metabolic chain. So at some point pyruvate has to go into acetyl-CoA. Biochemists will tell you what that is all about. But if you do it in pure water in a flask, you can see this part is unstructured. But if you do it in an actual biological system, you can see that part is unstructured because it doesn't have anywhere to bind. There's something else in the cytoplasm where it binds and then becomes structured. Such effects you can only see inside a simulation that involves the entire protein and the entire environment. Again, phosphoglycerate kinase, this is what synthesizes phospholipids. Acetyl kinase, some bacterial protein that puts the phosphorylation, phosphoric acid group onto acetate. And you can see there that that's the source molecule, that's the ATP that's bound inside in there. And then there's everything else around it, the rest of the cytosol, with the rest of the ATP. There's quite a lot of it in the cell, actually. That's some metabolites bound to the surface of some other enzyme. So the functioning of life at this level, you can only see inside simulations like this. And we do this on a daily basis in our actual research in computational chemistry division here at the chemistry department. Something else in there, I think that was interesting. This dramatic statement at the very end. All of this is actually precise atomic level simulations obtained with supercomputers. This one is not quantum mechanical, it's called molecular dynamics, but for the purposes of doing what it does, it's actually okay. And we will teach you to solve these equations on paper. paper, and we will give you a hint of how computers do it. There is a lecture on numerical methods. And of course, the next thing that we will cover in this module that you hear rather a lot about is artificial intelligence. There is a significant school of thought that AI will be the next dominant species on Earth. I happen to agree. So within the next 10 to 15 years, we will be demoted to the status of the monkeys. And life on Earth will be taken over by something that doesn't even need oxygen to live. So this is a neuron, and this is how it functions. It collects electrical signals from the various little appendages called the dendrites, and then when it decides that it became necessary, it sends a signal down the axon to other neurons. It is possible to make a mathematical model of that, where the signals that go in correspond to certain numbers. A big number is a signal of high amplitude, and so on. They go into some kind of summation and then some kind of activation function, this neuron head, and then they go to the output. And it is then possible to chain these mathematical objects together, and such a chain is called a neural network. And as you know, they are hugely successful in solving various problems that humans are traditionally good at, like image recognition, but deterministic programmed computers are not. It's a pretty old concept, actually. It appeared in the 50s, but what happened in the 50s is people said, well, okay, wow, this is the model of a neuron, let's make an artificial intelligence. There was a great big boom. But what happened is they didn't quite appreciate how many neurons you really need for something to work. And that's in the billions, and unfortunately, it was only about, again, 2015 that sufficient computing power has arrived for the neural networks to become practically useful, and hence this explosion that you see at the moment, where everybody's trying to make a neural network to do something, and the search engines like Google are so ridiculously efficient. I mean, they can give you the answer you were looking for from, some half-thought, half-formed query. They all use neural networks behind them. We use them in chemistry for digital signal processing, data classification, metabolite identification, and so on. That's a good example of how difficult that is. A modern processor, so in an expensive workstation, takes 43 days to train a particular neural network, in this case an image recognition one, and the various specialized cards that offload the mathematics do it in a couple of days. They are ridiculously expensive, these cards, so they're called Tesla cards. They do gazillions of multiplications per second, and they consume a couple of £1,000. But increasingly, I'd say at the moment this is as good as humans at many tasks that do not involve being sentient. In the next 5 years or so, they will start being sentient, and at that point it will get interesting. But again, this is something we do. Various nonlinear data analysis. So if you've got a bunch of infrared spectra and you'd love to know whether you've got a carboxylic group in your molecule, a neural network would be able to tell, even if human necessarily, well, not necessarily might. Then you've all seen sound voice recognition in your phones. It can tell you what tune is playing. It can do the dictation. This is a recurrent neural network that is sitting in there. In fact, Apple has started putting dedicated neural network circuitry inside the phones to accelerate that. And various other things, including solutions to things like Schrödinger's equation, can be done by neural network. This is kind of a joke, right? And not a joke because, of course, image recognition has become incredibly sophisticated. It can not only detect the hat, it can say that it has a white brim. This is Google's image recognition network. But then, of course, they can be fairly silly because they're not sentient. If you train a network to recognize dogs and you give it pasta instead, this is what it sees. Right? So there's a doggedness everywhere and it pops up the eyes. On the one hand, this is, kind of silly. On the other, of course, the psychiatrists who are dealing with schizophrenia have instantly recognized one of the symptoms. This is what happens to human vision when you have schizophrenia, and they suddenly gave us an insight about what we are, right? So we are, in fact, neural networks, you and I, and it would appear to show some similar features to what a broken human does. So, as I mentioned, colossal computing power is required. This is really only the last 3 years that this ever became possible to do these things. Things closer home, so this is my speciality of the research group that I'm the head of at Southampton, chemistry, magnetic imaging. There are complicated diffusion and hydrodynamics processes. In the body, drugs diffuse, blood movement in very many vessels is in fact turbulent. You have to do this magnetic resonance imaging that involves nuclear magnetization. That's a quantum mechanical process. The result being a rather horrible combination of hydrodynamics, chemical kinetics, and quantum mechanics at the same time, with another horrible equation describing all of that. That's the probability density of nuclear magnetization in the body. If any of you do a PhD, you'll probably find out what that is. But the important thing here is this is, again, a stupidly large differential equation. So you have an unknown function, you have a derivative here, derivative here, derivative here. So if you take all of these derivatives of this function and these derivatives, they're supposed to be equal, and what is the function that has that property? It's called the differential equation. I will teach you how to solve them in this course. Various complicated integral transformations that take frequencies and display them on a graph, things like Fourier transform, all of that will be covered in this course. Then chemical engineering is something that many of you are probably looking to do. Reactor design for complicated pharmaceutical synthesis, even something as simple as a microbrewery if you are making beer or whiskey. Or running a distillery, what you don't want to happen is some local temperature jump inside your reactor, which might easily happen if you have insulated the tube well. Or any silly chemical process, like an accumulation of a substance where it's not supposed to be, and then the yeast that ferments the beer either dies or becomes not too efficient, and your entire batch of beer is gone. So what you need to do is track reactor temperature in 3 dimensions, track the concentrations in 3 dimensions, see how they depend on temperature. All of that is computational modeling. And the exact subject that is about is called optimal control theory, and this is about controlling various complicated physical, chemical, and engineering systems in real time. One of the famous problems is landing a spacecraft. You have to give steering signals to the engine, to the various components in here. Well, thankfully it's outside the atmosphere, so you don't have to worry about aerodynamics in there, but you have to worry about fuel consumption. So, for example, a reasonable question that somebody might ask in engineering these days, what is the minimum possible amount of electricity that I need to produce this amount of aluminium by electrolysis? And of course, you all know that the minimum is 3 electrons per atom, but of course not all businessmen know that, and you get various, perpetual motion machine proposals. On the back of that, if you're ever doing serious engineering, you have to know what's possible and what's not. And again, this is something mathematicians call an optimization problem. This is finding the maximum possible value of a function or the minimum possible value, perhaps subject to some constraints, like total economic cost, or the highest temperatures of the reactor material can in principle withstand. So here, for example, the material is probably tungsten carbide or something, but it's not a good idea to push it above a couple of thousand degrees because it will simply melt. And the process of designing all of that is again a partial differential equation. It's rather hard to solve. So minimum time, minimum energy, minimum something else to achieve a certain objective from a certain initial condition. What you do is you create a system model, meaning mathematics. You expose user controllable parameters, steering signals in this case, but something as simple as sugar concentration if you're doing alcohol distilling. And then optimize them, and you obtain something called optimal control, and this is a functions that go into your steering machinery that ensure the maximum accuracy or the maximum efficiency or whatever it is that you have set out to obtain. So again, a significant mathematical problem. This is an example of how those equations look like. These are Navier-Stokes equations for hydrodynamics. This is what you need to solve if you are designing a ship, a submarine, or a re-entry vehicle for a spacecraft. This is what is going to happen because there is substance flowing around it. It's a compressible substance. There will be things like mass dynamics, so simple things like momentum conservation. There will be various angular momentum equations, how the body rotates, and there will be the energy balance. Obviously, if there's a chemical reaction, it might consume or produce energy, and you've got this horrible set of three-dimensional equations. They will not normally have analytical solutions, except in the simplest possible cases. You solve them on a computer, pixel by pixel, using numerical methods, and numerical methods of solving such things is one of the lectures in this course. Iris 5, the good old thing that my group spends rather a lot of time using. It's got about 500 nodes, and each node is about 10 times larger than your laptop in terms of computing power. So your typical node these days would have about 4 cores and about 4 or 8 gigs of RAM. These nodes have got 40 cores each and 200 gigs of RAM. They've got these super powerful Tesla V100 cards, which serve as mathematics coprocessors. Some nodes have about a terabyte of RAM, not disk, actual memory. And the amount of disk space that this thing has is measured in petabytes. So 10 to the, what is it? Not even 15, something like 18 bytes of storage. That's an example of a hydrodynamics calculation. This is what will happen if you put a heavier fluid, like water, on top of a lighter fluid, like acetone. Obviously, gravitation will push water down, and this is what is going to happen. This is called Rayleigh-Taylor instability, after the two mathematicians who have proposed an explanation for this. So clearly not a trivial process. And if you're a chemist who is studying such mixtures, you need to know about this. Where this often happens is in the ocean, where salty water, which is heavy, suddenly ends up on top of a layer of water which is either fresh or less salty, in which case the heavier water ends up on top of the lighter one, and the mixing process between the two layers of water looks exactly like this. If you have chemical reactions, and here it becomes even more complicated because the rate of chemical reaction is proportional to local concentrations, and then not only do you have a terrible mixture of concentrations, you have different reaction rates in different spots, and if suddenly you have a spot of high concentration of blue and a high concentration of yellow, what will happen locally is, of course, the temperature will go up, and you'd rather not it to end up too high. So the process of modeling all of that and making sure it doesn't blow up as a result, which is a very significant possibility. For example, in petroleum engineering, all of this is mathematical modeling. Where can you go after you've done something like that, done a project in computational chemistry? There is about 3 dozen companies here in Britain, and maybe a couple of hundred in the United States, that do computational chemistry, engineering, physics, and so on, and quantum mechanics or chemical processes for a living. This is a company, MathWorks, that makes MATLAB, the principal language that we use for mathematical modeling. It's absolutely enormous. It does everything from quantum theory to hydrodynamics. The installation alone is 36 gigabytes of disk space, so all of the functions, modules, blocks, and so on. And they have a headquarters in Cambridge, so just out of town. Go with this. They are very, very welcoming to students. NVIDIA is a company that makes these mathematics coprocessors. It's an American company. But this one card that goes inside your computer, which is smarketed, in fact, we just bought a couple of them for the research we are doing, is about 10 to the 13th multiplications per second. That's a ridiculous quantity. Particularly if you take into account the fact that about 100 years ago a computer was a lady downstairs who did 1 or 2 multiplications per minute. And now you're talking 10 to the 12 multiplications per second. So These companies are really useful because we are doing high-intensity computation. And along with the Iridis supercomputer, this is in fact what we are doing on a daily basis here, the chemistry department. Another thing that will be introduced in this course is something called Mathematica. You may have heard about it. It's a machine algebra system. This is something that will take your integrals analytically in letters. We'll solve your equations analytically and show you the solution process. It has a little neural network inside it, and it has a huge internal database of chemical data. So if you ask it to list all chemicals it knows about, it will give you a list of about 50,000 molecules and their structures, properties, everything you want. If you type in a simple chemical reaction, the neural network inside will realize you're talking about chemistry, switch it into chemistry mode, parse your input into the equations, give you that as an equation, and even produce basic thermodynamic parameters. What's the energy of this process, what's the entropy, and so on. Then you can ask questions in human language, which solvents are miscible with acetone, solvents it knows about, and so on. So this is a semi-intelligent system that will be able to solve most of the things that you have in our courses in the first, second, and third year. Just don't use it too much, right? You're supposed to train your brains versus some neural networks. So we are thinking about banning calculators as a mass examination, actually, because people are relying on them too much. So the thing that does this is called Mathematica, and this is one of the later lectures in this course. Alright, so before we go into the various technicalities, let me show you something that is truly real. So this is the screen of my workstation in the office. It's a remote desktop connection. The graphics isn't terribly good, but this is one of those industry-grade quantum mechanics modeling packages that we've paid a lot of money for. And let's just put a molecule in there. So methane, ethane, propane, butane. Rotate it on the screen. And let's put it into some unfavorable conformation. You know that staggered conformations in aliphatics are those when the atoms do not point directly at each other, they're kind of in between. So let me just push this molecule out of its equilibrium a little bit and then see what the program makes of it. So I'll choose this dihedral angle here and I'll rotate it a little bit into a clearly energetically unfavorable configuration. So what happens in here is the two metal groups collide. Remember that they're actually much bulkier than the steel plot shows. And you've got a bunch of hydrogens collided here. And what I'll ask the program to do is to actually rediscover the minimum energy configuration. So calculation setup, job type optimization, that means find me the energy minimum for this molecule. Method, one of those quantum mechanics methods. So we will explain what all of this is. Of course, about here you will be completely comfortable with that. Submit. Save. So it asks us to save this somewhere. So let's just save it on C. Some name. Submit for calculation. So this will not send it to a supercomputer because the molecule is small enough. It will be done locally. And so here's a program, and it will produce a colossal amount of output in there as it solves all of those quantum mechanics equations and minimizes the energy. And you can see coordinates flashing on the screen. This is the coordinates of each individual atom in there. Job completed. Do we want to close the window? Yes, please. And it will now load that thing. So let's see, open options, read intermediate geometries, and we would like to load this information. So it has taken 18 steps in how it returns a molecule to the energy minimum. You can see the conformation is now properly staggered. It has removed the collision. And if we look at the initial structure that we gave it, so this was collided. And then the first step it took it started moving, and then it eventually turned itself over. So if I make an animation on this, you can see that the calculation rediscovers the original moment. So a great amount of things happened while I was talking on this screen. In about 1990s, this would have been an overnight calculation. But the progress in computing power has really made it nearly instant. And things of this kind with much bigger molecules and much more complicated questions are what computational chemists do. So, all of this was nice and exciting. Some of the lectures that I will give you will be eye-glazingly boring, and there will be a lot of mass on this board here. But the reason I gave you this introduction is all this ridiculously boring math that Kuprov will be torturing you with is the mathematical foundation for everything that I've just talked to you about. So it will be tough, it will be boring, just bear with me, okay? When I'm teaching you how to solve second-order differential equations, it would not be a pleasant experience, except for the end objective of teaching you to use all of these things. Okay, now, so if you are into physical chemistry, computational chemistry, magnetic resonance, or AI, this is the module for you. 24 lectures, so 2 lectures a week. On this board with chalk and duster, so no PowerPoint anymore, taped. So this will be put on YouTube and the links will be posted to Blackboard. Do all the first years know what Blackboard is by now? Great, so you will find this lecture there now, and the video will be posted in the afternoon. The classes are 2 hours each, 1 class a week. The good thing this year is actually we were given a class slot that is after the lectures, so no inconvenience. It's quite good. 2-hour exam in January. All the first years present should have mathematics A levels. Second and third years have had all the necessary mathematics prerequisites already. That is, you've seen a derivative before, all of you, I assume. The exam has 3 types of things in it. The lecture content will have a lot of things like proofs. Derive this, demonstrate this, prove that. What will be done is one of those proofs we will ask of you. However, we do realize that it's impossible to memorize everything, so what I will do is I will post a list of 25 questions in this category to Blackboard, and one of those questions will appear in the exam. You don't know which, but if you've studied all 25 and you're comfortable with all 25, you are guaranteed to pass these first 25%. This is a continental sort of German/Russian style of teaching where you provide a long list of questions and you ask one. Right? If people work hard, they're guaranteed to pass, but by the time you've studied all of them, I might just as well give you maximum marks. Right? So it's an interesting balance. And then 50% of the marks is just some integral or some derivative or some simplification, trigonometric functions, and so on. And then 25% would be a problem from chemistry or physics, like chemical thermodynamics and so on. That's the structure of the examination. Most lectures will be me, so Ilya Kuprov, pronounced Ilya, and half of the classes will be done by Marina Krajeveta. We are both computational chemists. We specialize in quantum mechanics of magnetic processes, and would be able to more or less answer any question on any aspect of physical chemistry. So even if you have questions from some other courses, just ask them during the class. You'll find the office hours on Blackboard, and enjoy the module. So I'm telling you, it's going to be tough, but this is the cutting edge of what it means to be a chemist. So any questions on the exams and the technicalities? Okay, I'll see you on Thursday.